Hello, my name is Changkyu. I'm a PhD student at Rutgers University who is supervised by Professor Abdeslam Boularias. I'd like to talk about the learning to slide on an object with differentiable physics simulation. Let's say we have an unknown object on the table and we want to push it to the edge of the table first and pick it up from there. Then we should be very careful for not pushing it over the edge. Then basically we need to know the mechanical properties of the object. If we have a very high dimensional spaces, like if the object has a large number of components, it becomes very interesting in using the differentiable physics engine. We can start with playing with the objects and then we observe how they are moving. The next step is to take each object and decompose to a large number of cuboids. Each cuboid becomes individual object that is attached to adjacent cuboids. The differentiable physics simulator outputs the state at the time t plus 1 as well as the gradient of the state. Using these informations, you can compute the gradient of the reality gap and you can use the gradient to update the physics parameter. Recently, it has been observed that a standard physical simulation, which is formulated as linear complementary problem, is also differentiable and can be implemented in Python. We propose the modification of this work. We formulate the system as a linear complementary problem, and what we have in this equation is the mass and inertia matrix and two Jacobians that corresponds to internal forces and the frictions as the function of their velocity at time t. This describes the internal forces that are happening inside of the object, and we also have the frictions, which are external forces applied from the support surface. We also have the predicted velocity, the external force, the mu, which is the vector of the frictional coefficient. So you can solve this linear complementary problem, and this is how you forward the simulation. We analytically derive the gradient of the loss in closed form. It looks very complex, but it is nothing but the inversion of the diagonal matrix and the product of matrices, so it can be solved in polynomial time. And then we can do the gradient descent, and the last step is to put the upper bound on the maximum mass. Basically, this can be seen as inductive bias. We can do the same thing with the frictions, and then finally we can identify the mass and the friction of the cuboids. These are some result of the model identifications. If you look into the objects, some parts of the objects are heavier than the other parts. This could be very difficult to tell from the vision, but the proposed method managed to find something close to true mass distribution from the motion. It is not exactly, but I think this is due to the fact that we are using only very small number of examples, which is necessary for on-the-fly model identification on real time. These are different learning curves with different amount of training data. We compare the proposed method with a number of black box methods as well as automatic differentiation in Python. As you identify the model, you want to do something with it. So you want to get this hammer to the goal. But the problem is how to select the goal configuration. Based on the identified mass distributions, you can choose the stable goal configuration like this. And then you want to plan by generating waypoint poses using, for example, RT algorithm. The question is how to go from the one pose to another one. You can start with your best guess, and you can try to vary the contact points and see their changes. Then you can choose the points which is locally optimum, and then you can apply the actions to the real object. Here's the pre-aggressive sliding manipulation experiment. The left side is the one with uniform mass distribution of the hammer, and the right side is the one using our proposed method. All of these done autonomously without any interference in both identification of mass and friction, selecting the goal, planning, pushing and grasping object. All of these are done autonomously. This is our quantitative result of the same experiment, the percentage of the successful grasp in the end. As you can see here, putting upper bound helps a lot, because if you don't put it, then the observed motions are explained by the high friction as opposed to high mass. As you can see the experimental result, it is almost unavoidable to do this kind of mass identifications. Otherwise, we cannot reason about the stability of the object. So I think this work is quite important.